So the other week I looked at using the zip command to zip together a bunch of images. And at the time I was using the CFExecute tag built into ColdFusion, which means that I couldn't have relative paths in my resultant archive file because in order to do that I need to execute the zip command from within a working directory. And CFExecute doesn't allow for working directories. But what you can see in this version is that I'm actually prefixing all of my archive file paths with this myCoolImages folder, which is a relative folder, and I'm able to do that because in this case I'm actually using the ProcessBuilder instead of the CFExecute tag to run my zip executable. Now, I've never used the ProcessBuilder before. I've been inspired by Bradwood, who says he uses it all the time. So this is my look at using the ProcessBuilder to execute the zip command. So let's jump into the code and see what's going on. So first, just to paint the picture, essentially I have the myCoolImages folder, which is located at path to myCoolImages folder. So I've created this process command function, which takes the command name, zip in this case, the arguments to pass to that command, which are all the zip arguments. So this is kind of inspired by the CFExecute approach. I also have a timeout in seconds, again inspired by CFExecute, but the real main difference here is that I can also provide a working directory, in this case path2, and that allows the zip command to execute from a given working directory, which then allows us to use a relative path for my input file, which allows us to create a zip archive that has a relative file path within it. So how does this process command work? So process command here is going to be using the Java ProcessBuilder class, and you can see here I'm building up an array of the command name plus all of the command arguments, stringified just to make sure that the right data types. And the trick here is that the working directory, which is what I'm passing through as the argument here, is being used to call this .directory on the process builder. And what that's going to do is when we eventually call .start to spawn the child process, the process builder is going to be using this directory as the working directory for that process initialization, for that process execution. If we don't provide a timeout, then it's just going to start the task and not wait for it to actually finish, and it's going to return kind of this empty result, this null result object. But if we do have a timeout, which in this case you'll see, where is it? I'm waiting up to 5 seconds. In that case, what we do is we're going to combine the error streams and the output streams just to make it a little bit easier for us to reason about this process. And then we'll go about writing the output to a given temp file. Now it turns out there's a little bit of a catch-22 here in the way ProcessBuilder works. It provides this wait for method, which allows us to block and wait for the task to finish for up to the given number of seconds. But the problem is this is a blocking operation, but if the input stream of the sub-process fills up before we call wait for will actually never run because the input stream gets filled and it blocks the wait for itself. So what we're going to do is redirect the output of the process builder to this temp file, right, to this temp file that I've created here in my temp directory. That way we don't have to worry about the input stream blocking the wait for, and we get to call the wait for, giving it a timeout that we're gonna terminate the thread. And you can see here it'll wait for up to that seconds, and then it'll tell you whether or not that process ended within that amount of time. If the process hasn't ended and we've decided to terminate on timeout, you can see I can call destroy forcibly, and then we can get the exit value from that child thread, and you can see that's what I'm returning here in my result. The exit value from the sub-process, I'm reading in the content from that temporary file that we redirected the output to, and then I'm also returning the duration, and then finally I'm deleting that output file. And that's the values that we're seeing here. The code, so it exited successfully with code 0, took 500 milliseconds, and then here's the output that it generated. Now, I don't love the idea of using the intermediary file because I've been actually burned quite a number of times by weird file locks in Cold Fusion where you try to use a file that hasn't been quite created yet, you try to delete a file that a process still has a lock on, and you get errors that seem to be not reproducible or intermittently problematic. So I'd like to be able to do this without using the temporary file. But again, we have this sort of catch-22 where the input stream can block the wait for, which means that we want to read from the input stream first, but we don't want the input stream to block the wait for, but we want the wait for not to block the input stream because catch-22. So the other approach that I came up with was being able to use parallel iteration in Lucee CFML. So in this approach, all the stuff is exactly the same, exactly the same, exactly the same. The difference now is how we now handle the case where we have a timeout. So what we're going to do is just kick off the child process, and now what we're going to do is create an array of what I'm calling units of work. So you can see that this array is just lambdas. So I have one lambda here and then another lambda here. I guess closures, depending on how you want to call them. The first unit of work implements the wait for, right, to give the process a particular timeout. It then manages the forcible destruction of that thread if it hasn't completed in time, and returns the exit value. The second unit of work manages reading the input stream, and instead of writing to a temporary file, we're going to use in-memory stream consumption using this buffered stream reader, and you can see here I'm getting the child process's input stream. We're just going to keep looping while the read line returns a usable value, at which point we end up just returning the listification of the lines within that output. So again, we have two units of work. One unit of work is managing the duration of the process. The second unit of work is managing consuming the input stream. Now, we're going to ask Lucee to map over these units of work in parallel. So it's going to run those two lambda functions, those two closures, in parallel, one managing the duration of the process, one managing the output of the process. And because they're running in parallel, they're not going to block each other, which means that when this one's running, it's going to be consuming the input stream, which means that this wait for in the other thread shouldn't ever be blocked by a completely filled up input stream. And because this is running in a thread, the wait for shouldn't end up blocking the other unit of work, which is doing the input stream consumption. At least this is all my theory here. And then once we finish executing both of those units of work, you can see that now the code, the exit value, is just the result of the first unit of work, and the generated output is just the result of the second unit of work. And if we jump over into the other browser and we refresh, this is PB2, you can see we get the same exact output. So, and we can see actually, so let's just show that this is working. If we now go up here and instead of waiting for 5 seconds, we wait for 0.2 seconds, right, which is less than what this usually runs for, right? And now we refresh this, you'll see that it exited with code 137, which I don't know anything really about Unix exit codes, but that apparently is some sort of like sig kill or something like that, or sig terminate. And you can see we have no output, and it ran much faster, right? So pretty cool. And just to give you another little demo here, let's grab another command just for funsies, and let's paste that in here. So this is just going to do the ls command, and this is really just to show that the working directory is doing its thing, right? So we're going to be executing this from a parent directory. The ls, the list command, we're going to be passing in all, and I can't remember what all these stand for. And we can run this, and here you can see, so here are all the files in the current working directory. Right here is the first demo, PB. Here's the demo we're looking at now, PB2. And you can just see it works. So ProcessBuilder, pretty cool. This is the first time I've ever seen it until before Brad Wood had mentioned it. It's the first time I'd ever even heard of it. So take this with a grain of salt. I'm sure there are edge cases here that I'm not considering, but so far it seems like a pretty cool alternative to CF given the fact that we can use this working directory to change the way our executables work. And definitely we'll be using that in the future.